Hello, this is Andy from the Engineers Academy, and in this video we're going to look at how we take our UTS test data and turn it into something usable. Now, if you've watched the previous video on the ultimate tensile strength tests, then you'll know that the data that we're generating was the change in length of the test piece and the force applied to the test piece. Now, the problem with those two pieces of data is they don't take into consideration the dimensions of the test piece itself, and in particular the cross-sectional area and the length of the test piece. Obviously, the longer the test piece is, the more we would expect it to stretch relative to its length, and the greater the cross-section of the test piece, the greater force we would expect it to withstand. So it makes it very difficult to make comparisons between two materials when the samples aren't exactly the same size. So what we're looking at on the screen here is a raw data file from a UTS test on a sample of 70/30 brass. Now, the only additional information that I've added here is what can be seen in yellow, and I'm going to populate these yellow boxes in order to help us to generate some new columns for our data. Now, in order for this data to be usable, what we need to produce is a stress-strain graph. So we need to create two new columns, one for stress and one for strain. Now, also from the raw data seen in the three columns on the left-hand side, we're not particularly interested in the time taken for the test. It won't influence our stress and it won't influence our strain. So what I'm going to do is I'm going to remove that column, and in its place I'm going to add two columns, one for stress and one for strain. Now, I'm actually going to put the strain column first, and the reason I'm going to do that is that on a stress-strain graph, strain goes on the x-axis and stress goes on the y-axis. So it'll just make it easier when it comes to producing our graphs. So we've got strain and we've got stress. Now, hopefully you recall that strain doesn't have any units. It's change in length divided by original length, and a length divided by a length is dimensionless. So underneath here, where we've got the units, I'm just going to put a dash. And for stress, normally the units are pascals, but because of the significantly large numbers we're going to get for this, we're going to convert all of those to megapascals. Okay, so before we can populate these two columns, we need to add some information about our test piece. And the test piece used for this 70/30 brass test had a diameter of 5mm and a length of 27mm. So we can add that to these data fields here. Now, a diameter of 5mm is the same as a radius of 2.5mm, but we need to convert that to meters. 2.5 divided by 1,000 is 0.0025. So all I've done is half 5 to get 2.5, and then divide by 1,000 to get from millimeters to meters. Now, in this last box for area, our test piece was circular, and the cross-sectional area of a circle is pi r squared, pi times the radius squared. Now, I've already copied the value of pi to my clipboard, so I'm going to do equals, Control V for paste, and that value of pi was taken from Google. Times the radius squared. Now, the symbol that we use for times on Excel is Shift 8, the star. Radius squared, I'm going to click on the radius cell, and for to the power of, we do Shift 6, it's the hat symbol, and squared is to the power of 2. So all I've done there is pi times the radius cell raised to the power 2. And when I hit enter, I have the value of my area of 1.9635 times 10 to the minus 5. Okay, so we have all of our important information here. Next, we're going to populate our strain column. Now, strain is change in length over original length, or in this case, displacement of the chucks over original length. Now, displacement of our chucks is shown in column B here, the distance. This was the distance between the two chucks after we'd zeroed the displacement. So displacement over original length, I'm going to use a formula, and that formula is going to be equals. I'm going to click on the cell B4 because I want the strain that corresponds with that particular displacement. And I need to divide that by the original length, which is 27mm. Now, here's the important thing. because those displacements are in millimetres, I must use the length in millimetres. Now the reason for that is because strain is a relative value. It's a distance over a distance or a length over a length. We need to make sure that the units are consistent. So if we're using millimetres for our units of displacement or distance, then we must use millimetres for our unit of length. The alternative would be to convert both to metres, but those units must be consistent. So now we have our strain value, or we have our formula for our strain value, and I need to copy that all the way down the column. Now, one way to do this would be to drag this square down, and as we do this, you'll see that the data begins to populate. The displacement values are all 0 up to here, but now when I let go, it pastes those values down for the strain. But because there's such a significant amount of data here, I'm going to do something a little bit different. What I'm going to do is copy that cell using Control-C, and then I want to paste that cell down this full column. So I've clicked on the first cell here, and normally you can hold down Shift and click a lower cell and it highlights all of that column, like so. But I need to highlight the whole column, so I'm going to click back on the first cell and I'm going to scroll all the way to the bottom of my data using the scroll bar here, which is much quicker. So I scroll all the way down to my very last row. I hold Shift. You must remember to hold Shift to highlight all of these cells, and left click again, and you see it highlights all of that column. And then I can just do Control-V, and it will paste that formula down that full column. We'll just scroll down and check, and we can see that that's pasted the whole way down. Now we can repeat that process for the stress column. Stress is force divided by area. So I'm going to click equals. Force is A4, so I'm going to click on the A4 cell. And then as we paste that formula down, A4 will become A5, A6 and so on. So it will give the stress that corresponds with the force in that left-hand column. I need to divide that by the area. And I could type this in manually, 1.9635 times 10 to the minus 5. But instead, I'm going to click on that cell. Now the difference here is, when I paste that formula down, I don't want this cell G3 to change. I don't want it to become G4 or G5 because there's no information in those columns. So we can use something called absolute cell reference. And the way that we do that is by putting a $sign in front of the G and a $sign in front of the 3, like so. Now I'll just show you what this does. Let's hit enter. And let's paste that formula down a couple of cells just to show you what's happening here. And if I click on cell D12 here, what you notice is that A4 has become A12, the corresponding force, but the area, G3, has remained as G3. I'm just looking in the formula bar at the top here, and that hasn't changed because we've absolute cell referenced it. Okay, I'm just going to undo that step, and I'm going to use the same method that we used previously. So I'm going to click on the cell that I want to paste down the full column. I'm going to do Control-C to copy. I'm going to click on the cell directly below, D5 there, and I'm going to scroll all the way to the bottom. I want to highlight that entire column. I then hold down Shift and click on the bottom cell, like so, and then Control-V will paste that formula right down to the bottom of the cell. Now what we can see I've forgotten to do here is to convert from pascals to megapascals. So we're going to end up with numbers that are way too large. So I'm just going to make one modification to my formula. I'm going to click back on my top cell. And I'm going to put brackets around what I've already inputted. So A4 over $G, $3. And if I want to convert from pascals to megapascals, I need to divide by 1,000,000 because there's 1,000,000 pascals in a megapascal. So divide, 1,000,000 is 1 with 6 zeros. 1, 2, 3, 4, 5, 6. Enter. Now I'm going to recopy the new formula with the amendment, Control-C. I'm going to click on the top cell. I'm going to scroll all the way to the bottom. It doesn't matter that there's already data there, it's just going to overwrite it. I'm then going to do Shift and click on the bottom cell and Control-V. There we go. We can now see that that's amended, dividing those values by 1,000,000. So if we scroll down to where we've got a few more values, there we go. We can see that the megapascal stresses have been populated. Okay, now we're in a position to produce our graph, because if you recall at the start, I said we wanted to produce a stress-strain graph. We put strain in the C column because that's going to become our x-axis, and we put stress in our D column because that's going to become our y-axis. So we're ready to produce the graph. Now to produce the graph, we need to highlight all of the data in them two columns, and we're going to use a similar method to what we used previously. We're going to highlight the top cell in each column, here and here, and then rather than drag down all the way to the bottom of those two columns, I'm going to use the scroll bar on the right, and I can hold Shift and click on the bottom right box, and you can see it's highlighted those two columns. Now, the type of graph that I need is a scatter graph, and the reason it's a scatter graph is because I want to plot those two columns against each other. So I'm going to go Insert. Under Charts here, we're looking for this one here where we can see a small diagram of a scatter plot, and when we hover over it, it says Insert Scatter, X, Y or Bubble Chart. If we click the small arrow, I'm just going to use the line, and the reason I'm just going to use the line is we've got a significant amount of data here. If we went for the dots and the line, or just the dots, then all of those would blend into one. It would become very cluttered on the diagram. So I'm just going to use the line. And there we have our stress-strain diagram. We have stresses in megapascals, and we have our strain along the bottom. I'm just going to move that chart to the top, and the way that I'm going to do that is I'm going to cut it from its current location. I'm going to scroll all the way back to the top. You'll see why I'm doing this in a moment. And I'm going to paste it under these yellow boxes here, so Control V. And the reason why I've done that is so that we can refer to some of this additional information at the top here. Okay, so the next step is to add a title and legends to our chart. So if you click on Design in the menu at the top, and then go to Quick Layout here, we can decide what kind of layout we want. Now I'm going to go for something very simple, just with the title and axes labels. I'm going to remove this label here for the series. So the title can be Stress-Strain Graph. For 70-30 brass. On our x-axis, if you recall, we have strain. We don't need to put any units on that because strain is dimensionless, it doesn't have any units. And on our y-axis, we're going to put our stress, which is being measured in megapascals. So now we can use this graph to find a couple of things. First of all, we're going to find our yield strength. And secondly, we're going to find our ultimate tensile strength. And the way that we're going to find our yield strength is by looking for the point where elastic deformation became plastic deformation. Recall that elastic deformation is where the test piece would spring back to its original length when the force was removed, and plastic deformation is once it's permanently deformed. And there's a very easy way to identify this from the graph. If we look at our graph here, we have a curved section. Now this is typical because it takes a while for the test piece to pick up the tension when the chucks start to move. It's basically the point where tension begins to go onto the test piece. And then we have a linear section. This linear section between maybe 50 megapascals up to around 190 megapascals is our elastic region on our graph. So what we're looking for is the point where elastic deformation, or this straight section, becomes plastic deformation, or this curved section. Now we could look at this and say it's roughly 180 or 190, or what we can do to be more accurate is hover over the point on the graph. See, if I hover here, we can see that the stress corresponding with that point is 186.06 megapascals. I'm just going to go to the nearest megapascal, and so the yield stress at that point is 186 megapascals. Yield strength and yield stress are the same thing, they're interchangeable. 186 MPa. Now we can do exactly the same to determine our ultimate tensile strength, or our ultimate tensile stress, because that's the highest stress value that's reached on the graph. So we're looking for the highest deviation in the y-axis. Now once again we could look at this and guesstimate at around 450, or we can hover over our highest point, which I think's around here, and we get an answer of 452 megapascals. You might want to check along and see if you can find anything higher, but 452 appears to be the highest point, and I hover here, 452 megapascals. So our UTS is 452 MPa. Now the last thing that we can use this graph for is to find the elastic modulus of the 70-30 brass. Now hopefully you recall that elastic modulus is stress divided by strain. But when we look at this graph, we've got lots of different stress and strain values, and in actual fact the elastic modulus only applies in our elastic region here. Now the reason we can't just use any stress strain value off of this is because this linear section doesn't go through zero. Remember we had this kind of pickup of tension here with this curve. So instead what we need to do is we need to take the gradient of this straight section. Now again that may sound a little complicated, but what we can do is what we've just done previously. We can hover over points on the graph to determine the x and y coordinates of given points. I've just written up the top here, elastic modulus is stress 2 minus stress 1. So we're going to pick 2 points. One point will be at one end of the elastic region, and the other point will be at the other end of the elastic region. So we have stress 2 minus stress 1. Well, that would represent our change in the y-axis, delta y. And epsilon 2 minus epsilon 1, the corresponding strain values, would be equivalent to our x-axis, change in x. So how are we going to do this? Let's hover over a point at the end of our elastic region. And here we can see that the stress is 186 and the strain, let's do this to 4 decimal places, is 0.1293. So epsilon 2 is 0.1293. And the corresponding stress there was 186 megapascals. Now point 2 is the highest point. Point 1 is what we're going to look at next. So if we hover somewhere else on that linear section, and I'm going to go around here, again we're going to end up with a set of coordinates. Here our stress value is 70 and our strain value is 0.1020. So 70 and 0.1020. So now we're in a position to calculate our elastic modulus. So let's add it underneath our UTS here. So we've got elastic mod. You may also see this called Young's modulus. It's exactly the same thing. And our formula is U2 minus U1 in brackets divided by epsilon 2 minus epsilon 1, the formula here, change in y over change in x. So we can do this with a formula, equals, open brackets, stress 2, we're going to click on the 186 cell, minus stress 1, we're going to click on the sigma 1 cell with 70 in it, close brackets, divided by, open brackets, epsilon 2, again we're clicking on the cell with that value, 0.1293, minus the cell with epsilon 1, 0.102. We've lost a 0 off of there because 0.102 is the same as 0.1020. But anyway, we'll click on the cell, we close brackets, and then we hit enter. and that gives us our elastic modulus. Now that represents our elastic modulus in megapascals, and the reason for that is because our stresses are in megapascals. Now typically you would express elastic modulus in gigapascals. So how we would get from megapascals to gigapascals is by dividing by 1,000. So again, I'm just going to use a quick formula. I'm going to type equals. I'm going to click on my elastic modulus in megapascals and just divide it by 1,000. And there I have my elastic modulus in gigapascals. Now, if you're familiar with elastic modulus and the values for typical materials, you'll notice that that value there is very low. And there's a couple of reasons for that which relate to the way that the test's conducted. We won't go into the details of that in this video, but it is something that we will explore if you study the HNC materials unit with us. Anyway, I hope you found this video useful, and thanks for listening.